Today we're going to continue our study on Pascal's triangle and see how it's going to help us expand binomials. So we're going to use it in the binomial theorem to expand binomials. So let's talk about what that actually means. So up till now we have had problems like x plus 3 and I've asked you to square them or I've asked you to cube them. Either way, what that would mean is that we would have to take x plus 3 times itself either 2 or 3 times. So that means we would have to use a process of distribution or foiling to complete that task, which would give me x squared plus 3x plus 3x plus 9, and then we would simplify this to x squared plus 6x plus 9. If I continued to change that and make that a cube, now we would have to multiply again. But what Pascal's triangle is going to help us do is to alleviate all of that multiplication process. So if I ask you to take x plus 3 to the 10th power, it would not be so cumbersome because we would use the patterns within Pascal's triangle to do that. So let's recall how Pascal's triangle is built. So it's built by the understanding that all of our outside edges are 1s. And then to replace the value underneath in the triangle, we take a summation of what comes before it. So this next row would give me 1, 2, 1. 1, I add together 3, 3, 1. 1 with addition, I get 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. And I just continue the summation process all the way down until we get a triangle that looks like this. Now remember that Pascal's triangle doesn't end. It continues to grow to infinity forever. Now to understand some properties so that when we start to expand our binomials, you know what we're going to be talking about. This initial row right here, we're going to call this row 0. We're going to call this second line really row 1. So we're not starting at the first row, we're starting at ground 0 and then go to row 1, go to row 2, row 3, row 4. So when we're doing our expansions, our exponent is going to be equivalent to the row that we're going to use. All right, so how does this work? So when I expand binomials, I'm looking for when I multiply a binomial times itself n times, what my result will be. Well, what I'm going to use is a process from the Pascal's triangle. So when I ask you to take a plus b to the 0 power, that's going to simply give you 1. We learned that property when we talked about exponents. Any number to the 0 power is going to be assumed to be 1. So that comes from row 0 here, to the 0 power. Now, when I ask you to expand a plus b to the first power, well, anything to the first power is just itself. So in essence, what we have here is we're going to be working in row 1, and we're going to have 1a plus 1b. Now we know that that is simply just a plus b, but for our process of understanding the patterns, we're going to write it as 1a plus 1b. Now here is where we would have to start to multiply. A plus b to the second power is really a plus b times itself. But we're going to actually look in row 2 here for our coefficients in our binomial expansion. So notice that I'm going to have 1a squared, I'm going to have 2ab, and 1b squared. Now as we walk through this process, you're going to see this pattern develop. So a plus b to the third power, we're going to use this row here. We're going to have 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Noticing some patterns here is that I'm always going to have the coefficients that show up in the triangle. Those become my coefficients. Then my expansion of my exponent's always going to add to be 3. See, I have a cubed, I have a squared b, that's 3, ab squared is 3, and b cubed is 3. But what's happening here is I'm going to start with my first variable, a, and I'm going to lower it each time. A cubed, a squared, a, then I don't have an a. The b's I'm going to raise each time. No b, b to the first, b to the second, b to the third. And we continue that pattern. If I expand a plus b to the fourth power, I'm going to be looking in my fourth row here. 1, 4, 6, 4, 1 are going to be my coefficients. Then I'm going to walk through my exponents. So 1a to the highest exponent plus 4 is my coefficient. I'm going to lower my a. I'm going to raise my b, all the while keeping the exponent degree to be 4 in each term. Plus, my next coefficient is 6, lower my a, raise my b, plus 4, lower my a, raise my b, plus 1. When I lower my a, I go to a to the 0 power, which I can just make it 1, and I raise my b to the final power of 4. So all of my powers equal 4, and you can see my coefficients that I have taken from Pascal's triangle. So we can skip. Let's just watch what happens in a to the 6th power, a plus b to the 6th power. So I'm going to look at the 6th row here. I'm going to end up with 1a to the 6th plus 6a to the 5th, lower the a, raise the b, plus 15, lower the a, raise the b, plus 20, lower the a, raise the b, plus 15, lower the a, raise the b, running out of room here, plus 6, I'm going to pull this down here, lower the a, raise the b, plus 1, and I lose the a, and my b goes to its highest power of 6. So that you can see my coefficients. My coefficients are 1, 6, 15, 20, 15, 6, and 1. All the while, each add to be 6. 6, 6, 6, 6, 6, and 6. And that's how we expand our binomials using Pascal's triangle. So if I come down here in this section and I want to know what's different when there's a minus, well, what happens is that second term has that negative to it. Now, instead of involving the negatives, a good pattern to see is that the first number is always going to be positive no matter what. And then the terms are always going to flip-flop. Okay, so a minus b squared is going to have the same terms as this guy here, a plus b squared, but what's going to be different is the first term is going to be positive, 1a squared, then it's going to flip to be negative 2ab, and then the last term is going to be positive here, plus 1b squared. If I go to a minus b to the 4th, it's going to be the same as this guy, but I'm going to flip-flop my terms. So it's going to be 1a to the 4th minus 4a cubed b plus, so it's going to be positive, negative, positive, 6a squared b squared minus 4ab cubed plus 1b to the 4th. All right, now when you have actual numbers in there, then you're going to have to simplify the numbers, and we're going to see how that works. So let's look at this patterns in any binomial expansion. So here are the properties. It says, first of all, there are n plus 1 terms. So if I go back here, if I'm raising it to the second power, I have 1, 2, 3 terms. If I'm raising it to the fourth power, I have 1, 2, 3, 4, 5 terms. So there's always one more term than there is in the power. The exponent, n, is the exponent of a in the first and b in the last term. If I go back, when I did the sixth power, the first term has a 6, the last term has a 6. But each one always adds to be 6 also. In successive terms, the exponent of a decreases by 1 and the exponent of b increases by 1. So we decrease the a, we increase the b. That's the first term versus the second term. The sum of the exponents in each term is n. I've repeatedly said that. And the coefficients are symmetric. They increase at the beginning of the expansion and decrease in the end. And that's because our triangle is symmetric. So you can see that these are my coefficients. They are getting bigger and then they're getting smaller as we go to the other side. Okay, so let's look at some problems when they're not always just a plus b's. So this is t plus 3 to the fifth power. So what you want to do is have that triangle handy. And I'm going to first write down what my coefficients are going to be in the fifth row. So the fifth row, my coefficients should be 1, 5, 10, 10, 5, and 1. So now I'm going to use those with these two terms. Now this becomes my a, and this becomes my b. You can see that my terms are not always a's and b's. So we're going to have 1 times t to the fifth power plus, so this is a plus, so all of my terms are going to be plus. 5 times t gets lowered, and then the 3 starts raising. So you can see I still have 4 plus 1 is 5. Plus, my third term is 10. T gets lowered, the 3 raises. Plus, 10 times t gets lowered, 3 raises. Plus, 5 times t gets lowered, 3 raises. And my last term is going to be 1 times 3 gets to its highest power of 5. So I can see here, I'm raising it to the fifth power. I have 1, 2, 3, 4, 5, 6 terms. So now the last thing I'm going to do is go through and simplify and do my exponents and multiply. So I'm going to end up with t to the fifth power plus 3 to the first times 5 is 15t to the fourth. Plus, then I'm going to do 3 to the second is 9 times 10 is 90t cubed. So I'm going to mark these off as I simplify. 3 to the third is 270 times, 3 to the third is 27, times 10 is 270. I got a little ahead of myself. T squared. Then I'm going to have 3 to the fourth power, and I'm going to take 3 to the fourth power times 5, which gives me 405 t, that's this power. Then my last term is simply 3 to the fifth power, which is just 243 times 1. So this, if I were to expand t plus 3 and multiply itself by itself 5 times, I would end up with this polynomial. Okay, let's look at expanding y minus 4 to the sixth power. So the first thing I'm going to do again are write my coefficients from the sixth row. So what I can do, so I have 1, 6, 15, 20, 15, 6, and 1. Noticing that this is a minus, right now I'm going to write what my terms are going to be. That means this is going to be a minus 6, a plus 15, a minus 20, a plus 15, a minus 6, and a plus 1. So that way I don't have to worry about expanding those negatives along the lines. That's what my polynomial will end up being. So I'm going to start here. I'm going to take 1 times y to the sixth power minus 6 times y to the 5th times 4 to the 1st plus 15 times y to the 4th. So you can see my y's walking down, 6, 5, 4, and now my 4's are going to start raising. 1, 2. Then I have minus 20, y walks down, 4 walks up, plus 15, y is lowered, 4 is raised, all the while keeping 6. 5 plus 1 is 6, 4 plus 2 is 6, 3 plus 3 is 6, 2 plus 4 is 6, minus 6 y to the 1st times 4 to the 5th plus 1 times 4 to the 6th power. And then we're going to go ahead and multiply that out. So that's first term just simply gives me y to the 6th. The next term is going to be negative 24y to the 5th when I take 4 times 6. Then I'm going to have 4 to the 2nd power, which is 16 times 15, is going to give me 240 y to the 4th. Then I have 4 to the 3rd times negative 20 is negative 1,280, and that's going to be y to the 3rd. That's my 4th term. My 5th term is 4 to the 4th power times 15 is going to give me 3,840 y squareds. And then I have 4 to the 5th power times negative 6 is negative 6,144 y plus 4,096 when I expand 4 to the 6th power. So it does take time, and it takes a little bit of organization to get that final polynomial, but it's still a lot easier than taking y minus 4 to the 6th power. Let's look at 2 more examples together. So we're going to expand 3x minus y to the 4th power. So I'm going to find my 4th row. My exponents are going to be 1, 4, 6, 4, and 1. Since this is a negative, this is going to be a negative 4, positive 6, negative 4, and positive 1 as we move to expanding. All right, now we need to be careful with that 3x because when we raise that to a power, we have to raise the 3 with it, not just the x. So this becomes 1 times, so I'll use parentheses here, 3x to the 4th power minus 4 times, lower the 3x by 1, raise the y to the 1st, plus 6. Take our first term and lower it, take our second term and raise it, minus 4. First term lowers, second term raises, plus 1, and I lose my first term, 4, 3, 2, 1, 0, and I gain 1 more in my last final term. So now I need to make sure that I expand that 3 along with the x. So this term's going to be 3 to the 4th power, which is 81, x to the 4th power. This here, I will have 3 to the 3rd power times negative 4, which is negative 108 x cubed y. So I don't want to forget about my second term. Plus, I have to square my 3, so that's going to give me 9 times 6 is 54 x squared y squared. My last term, so I have 1, 2, 3 so far. My 4th term is going to be 3 to the 1st times negative 4, which is negative 12 xy cubed. And my last term is simply y to the 4th power. So I have 1, 2, 3, 4, 5 terms when I am done. All right, my last one has not only a coefficient in there of 2, but I also have a fraction that I've got to practice and work out. You can see that I'm raising it to the 4th power, so my coefficients are the same as the last problem. What's different is this is a plus. That means they're all going to be pluses. So I'm going to work this problem like the last one, except now I have a fraction in there. So I'm going to have 1 times 2c to the 4th plus 4 times 2c to the 3rd times 1/3 to the 1st plus 6 times 2c to the 2nd times 1/3 to the 2nd plus 4 times 2c to the 1st times 1/3 to the 3rd, all the while making sure my exponents add to be 1, plus 1 times, and I only will have the 1/3 in this term, and it will be to the highest power of 4. So now I'm going to work this out. So I have 2 to the 4th power as well as c to the 4th power gives me 16c to the 4th. Plus, I have 2 to the 3rd power times this 4 is 32. Now I'm going to have that over that 1/3, c to the 3rd power. Now over here, I'll have 1/3 to the 2nd, which is 1/9. I have 2 to the 2nd, which is 4 times 6. So this guy's going to give me 24, and that 9 is going to go to the bottom, c squared. Plus over here, I'm going to have 1/3 to the 3rd, which is 1/27. 4 times 2 is 8 over 27c to the 1st. And the last term is going to be 1/3 to the 4th power, and that is simply going to be 1 over 81. And you can see 1, 2, 3, 4, 5 terms when I'm done. So I'm going to ask you to do a couple of these problems on your own tonight to practice, and then we'll discuss your questions tomorrow in class. I hope you have a great day.